I present the paper. Contrastive learning relies more on spatial inductive bias than supervised learning, an empirical study. Self-supervised contrastive learning has shown tremendous potential in learning generalizable representations from unlabeled datasets, achieving comparable and even higher accuracy than supervised learning in various tasks. This inspires a lot of work aiming to understand how contrastive learning works. Previous work mainly focuses on its feature space downstream accuracy and loss formulations. However, there is no work aiming to understand which information or which inductive bias is exploited by contrastive learning when lacking supervision. In this paper, we design and conduct experiments to study inductive bias of contrastive learning. We show that CL relies more on spatial inductive bias than SL, and draw the conclusion that the spatial inductive bias is the key information exploited by CLs. In order to evaluate the dependency on spatial inductive biases, we designed two types of patch shuffling to destroy certain information. For global patch shuffling, we divide the image into patches and then shuffle them to destroy global structure. For local patch shuffling, we also divide the images into patches, then shuffle the pixels in each patch with the same permutation to destroy local structure. We quantify a dependency for a certain inductive bias by the performance drop after training on a dataset that saw that such information was destroyed for all the images. Our experiments on Sci-Fi 10 show that all the CL algorithms consistently rely more on spatial inductive bias than SL. We also observe that CL algorithms relies more on global inductive bias than local. The conclusion holds for all the backbones on the Sci-Fi 10 dataset, and also holds for the full ImageNet dataset, even more noticeable. We use TSNE to visualize the feature space of Moco V2 trained on Sci-Fi 10 under various corruptions. Moco trained on the original dataset provides a well-clustered feature space, which is desired by classification tasks. However, with a patch shuffle dataset, the boundaries in the feature spaces are less clear, showing that destroying spatial inductive bias undermines CL feature space. We also observed that global shuffling has a less separable feature space than local shuffling, consistent with the relationship between their accuracies. On the contrary, datasets with corruptions like defocus blur maintain all the spatial inductive biases, so its accuracy and feature space are very similar to the model trained on the original dataset, showing that spatial inductive bias is the only key information exploited by CL. We also use activation maps to show how the CL trained model changes after training on a patch shuffle dataset. When trained on original dataset, both supervised learning and Moco focus on the correct part of the image, even the corrupted ones. While trained on the shuffle dataset, supervised learning can still focus on the correct part. Moco, however, focuses on a continuous but incorrect part in the shuffled image, and even loses ability to deal with the original images. This shows that without global inductive bias in training, CLs are unable to learn to reason and understand images correctly. In conclusion, we are the first to observe, define, and analyze CL on spatial inductive bias. We propose the method patch shuffling to evaluate spatial inductive bias for learning algorithms. Using the patch shuffling, we perform extensive empirical studies on various tasks, for various learning algorithms and with various backbones. We also offer detailed analysis and explanations for all the observations, inspiring community to further investigate inductive biases in contrastive learning. Thank you for listening.